Welcome to this explainer. Today, we're jumping right into the underlying math of the ultimate theoretical cosmic monster, the Kerr-Newman black hole. You can kind of think of a black hole as having its own underlying source code, or like stats on a character sheet. And today, we're going to look at how physicists slowly built up those stats over decades to construct this absolute behemoth. Now, when we look at the iconic Event Horizon Telescope image of a black hole shadow, it's incredibly easy to feel a sense of absolute awe. I mean, we are looking at a region of spacetime where gravitational forces are so intense that nothing, literally not even light, can escape. And looking at that glowing ring of plasma, it really feels like the underlying physics must be infinitely complicated, right? So that brings up a really fascinating question. How much information does it actually take to mathematically describe this entire cosmic behemoth? If you wanted to write down the exact space-time geometry of what we're looking at, how many variables do you need? You might think you'd need to know the shape of the star that originally collapsed, its chemical makeup, its magnetic fields, or, all of its tiny irregularities.
But amazingly, the answer is just 3. According to the rules of general relativity and what physicists call the no-hair theorem, any astrophysical black hole, given enough time to settle down after gravitational collapse, actually radiates all that extra complex information away in the form of gravitational waves. What remains is completely characterized by just 3 parameters: mass, spin, which is its angular momentum, and electric charge. That's it. Just 3 building blocks for the whole shebang.
Now, physicists didn't just discover this complete picture all at once. By adding these theoretical building blocks one by one to Einstein's field equations, scientists mapped out an entire family of black hole solutions over the course of half a century. Let's actually go back to the beginning of this evolution and see exactly how this builds up to our ultimate black hole. We start with the base model, relying solely on mass. Back in 1916, just 1 year after Einstein published his theory, Carl Schwarzschild calculated the spacetime geometry of a static, non-rotating, uncharged mass, and this gives us the Schwarzschild black hole. It features a single, spherical event horizon. That's a one-way boundary where extreme gravitational time dilation means time literally stops for an outside observer. Deep inside that horizon lies a curvature singularity, a terrifying abyss where infinite density is crushed into a single point, and where the theory of relativity essentially breaks down. Shortly after that, physicists naturally asked, well, what if the mass has an electric charge? So between 1916 and 1918, the Reasoner-Nordstrom metric was developed. By adding charge to our stat sheet, the internal structure gets a whole lot weirder. Instead of just one event horizon, a highly charged black hole develops a complex inner boundary alongside the outer one, where the standard rules of cause and effect actually start to break down. Mathematically speaking, crossing this inner boundary opens up theoretical pathways to other regions of spacetime. Yeah, like a wormhole. But keep in mind, this model is still perfectly static and perfectly spherical. The problem with that is, real stars in our universe aren't static. They spin. So when a spinning star collapses, the resulting black hole absolutely must spin as well. But it actually took until 1963 for mathematician Roy Kerr to solve the equations for a rotating, uncharged black hole. The Kerr metric fundamentally changes the game here. Rotation breaks that perfect spherical symmetry and violently, dramatically warps the surrounding geometry of spacetime itself. And this brilliantly illustrates one of the wildest effects in all of physics, frame dragging, or the Lense-Thirring effect. A Kerr black hole doesn't just sit there in space, it actively drags the fabric of space along with it, kind of like a spoon stirring thick honey. If you are a local observer hovering near the black hole, and you fired your engines to stand perfectly still relative to the distant stars, this rotating geometry would physically drag you around the black hole anyway. No way around it. So the crucial takeaway here is that this severe frame dragging creates a brand new region of space called the ergosphere, located just outside the outer event horizon. Inside the ergosphere, spacetime is literally being dragged faster than the speed of light. No amount of rocket thrust can keep you stationary here. You are absolutely forced to orbit in the direction the hole is spinning. But there is a perk. Because the ergosphere is outside the event horizon, you could theoretically fly in, steal some of the black hole's rotational energy through a mechanism called the Penrose process, and escape back into the universe. The spin also completely transforms the core of the black hole. In our original Schwarzschild model, remember, we had a point singularity. But when you add rotation, the intense centrifugal forces actually stretch that infinite point out. The mass predicts a bizarre ring singularity instead, a spinning hoop of infinite density. It's totally wild to think about. Which finally brings us to the final boss of classical black hole physics, the Kerr-Newman black hole. By combining mass, spin, and electric charge, we arrive at the absolute most complete mathematical picture of a black hole floating in empty space. It has the inner and outer horizons caused by charge and spin, the frame dragging and ergosphere caused by spin, and that bizarre ring singularity at its core. It is the ultimate complete mathematical description. But how they found this ultimate equation is quite a story in itself. Given how notoriously difficult Einstein's equations are, you'd probably expect years of agonizing calculation. But hilariously, Ezra Newman, who published the metric with his team in 1965, admitted it was discovered largely by guesswork. They basically just took the Kerr metric, wrote down the obvious generalization to include electric charge, plugged it into the Einstein-Maxwell equations just to see what would happen, and incredibly, it worked perfectly on the first try. But here is the massive plot twist of our explainer. Even though the Kerr-Newman metric is the most complete and general mathematical solution allowed by the laws of physics, the universe seemingly refuses to let it exist. When astronomers look out into the cosmos, they definitely expect to find Kerr black holes with mass and spin, but they don't expect to ever find a fully realized Kerr-Newman black hole. So why is that? Well, it's because the universe absolutely hates a charged vacuum. Let's say a black hole did manage to swallow a bunch of extra electrons and acquire a massive net negative charge. That extreme charge would instantly and violently attract oppositely charged particles, protons, from the surrounding plasma, all while repelling further electrons. Thanks to this rapid discharge process, along with some complex quantum effects in the vacuum of space, the black hole rapidly neutralizes itself. And this neutralization happens on a timescale much shorter than anything we probe with our observatories. To put that into perspective, when we look at the light fading from the plasma around Sagittarius A star, the supermassive black hole right at the center of our own galaxy, the math suggests its electric charge is basically zero. It's a charge-to-mass ratio of less than 10 to the negative 18th power. So for all intents and purposes, it's exactly zero. This reality leads the astrophysics community to rely on what's called the Kerr hypothesis, shifting from the realm of hypothetical ultimate black holes to the practical reality of our universe. This hypothesis confidently states that all real astrophysical black holes we see in nature are just Kerr black holes, characterized solely by mass and spin. That electric charge parameter is effectively stripped away by the environment, leaving the Kerr-Newman metric as a brilliant but purely theoretical mathematical curiosity. However, we shouldn't close the book on this just yet. Advanced gravitational wave detectors and high-resolution imaging from the Event Horizon Telescope actually allow us to observe the shadows of these black holes and test the Kerr hypothesis directly. We are looking for any tiny deviations in the space-time metric. Why? Because theories beyond the standard model suggest black holes might carry exotic charges. For example, many-charge dark matter models propose particles with incredibly low charge-to-mass ratios compared to electrons. A black hole could potentially gorge on this mini-charged dark matter without triggering that rapid discharge process we just talked about, meaning a charged black hole could actually exist. And that leaves us with a truly exciting thought. As we peer closer to the event horizon than ever before, using shadows and ripples in space-time to measure these cosmic giants, we really have to ask, what if the Kerr hypothesis is violated? If we do eventually find a fully realized Kerr-Newman black hole holding on to an unexpected charge, what profound new laws of physics or hidden dark matter forces is it hiding? Thanks for joining me on this explainer, and keep looking up.